Okay, it's 3 p.m., but no one has turned up so far, so I'll wait for 5 minutes and then get started with my session. So I'll wait for a couple of minutes and then we'll start with today's session. Let's see if few more people join in. So meanwhile, can anyone confirm that you can see my screen and also can hear me? Yeah, hope I'm audible. So I'll get started in a couple of minutes. Let's wait for a few more minutes for a few more people to join in. Yeah, during today's session, it would be good if you keep your calculator with you or you use any other means to calculate some values, maybe Excel or something else as well. So that would be helpful. All right, I think I'll get started with today's session since it's already 3 past 3. So I think in this week's content is pretty easier compared to the other past 2 weeks' content. So this week I'll be discussing on single variable optimization and the related problems that you'll see in the assignments. And as you already know, I have already introduced myself in the previous two sessions. So I'd like to have it more interactive this session. So it would be good if you like answer some questions when I ask during the session. And also, if you have some questions, you can ask me at the end, like at the last 10 minutes. And also, if you have like any doubts when I'm solving a problem, you can interrupt and ask me questions as well. So that's not a problem. So let's move on with today's topic. So the things that I'll be discussing is first is the Newton Raphson method, and I'll be taking one example to solve a problem. And next, I think you have learned this two methods, exhaustive search method. So I'll be discussing one problem related to that. Another is the bounding phase method. So both of these are bracketing methods. And next, what we have is the golden section search method. Interval halving method, bisection method. So I guess you have all this 6 topics in this week's content. So I'll probably be solving one problem from this as well. So let's see how much I can cover. And Yeah, some parts I might try to solve in Excel, but otherwise I'll just calculate it. I'll write it down and probably will ask you to calculate some values for me. Okay, so let's get started with the first problem. So first is the Newton Raphson method. So I'm not going into the detail of the theory. I think you have already gone through the lectures and you'd already know. So the first problem that I'm giving is a function, say fx, uh, equals to say x square minus e to the power minus x. So find uh, the root of this equation. So there can be multiple, but using Newton-Raphson method, or maybe the interval that I'll ask you to find out where this fx function vanishes. So with x naught equals to 0.5, which is the starting value in your Newton-Raphson method, uh, using Newton-Raphson method. Okay, so let's try to solve this. So fx is x square minus e to the power minus x. And for Newton-Raphson method, what we need is f prime x is already also required. So it's 2x minus of minus e to the power minus x times minus 1. So it's 2x plus, yeah, something like this. So now, can anyone tell me what's the formula for Newton-Raphson method in terms of x naught? Now, what should be in the later part of this equation? So anyone can unmute and answer this. Yeah, I know it's pretty simple, this week's content, but it would be good if you solve it with me. Okay. Hope everyone is there in the class. Or you can use the chat as well. Okay. Okay. So I think no one is interested in interacting today. So let's go ahead. I'll just go ahead and solve it. So since it's pretty simple, so what you can do, you can write an equation like this. Then your fx naught is given as x naught square minus e to the power x naught. Then it's 2x naught plus e to the power minus x naught. So if you further simplify it, probably you don't need to simplify, but I'm still doing it. So it will be 2x square plus x naught, something like this. Okay, so it will be x naught square plus 1 plus x naught times. So this is your x1. So actually your x2 will be again in terms of x1 in the right hand side as well. You can write your xn plus 1 in terms of xn. So this will be a relation. Now it's just plugging in the values. So it's pretty simple actually. If you like start with x naught equals to 0.5, then probably you can do it in Excel as well, and then probably create a table like this. Say your xn and your xn plus 1, and this is your n. So when n equals to 0, This is your 0.5, and then you have to find your x1 using that formula. So, like if anyone had have calculated, that would be good, but otherwise, like I'll probably have calculated it before. I'll go ahead, or maybe I'll do it in Excel. I'll stop sharing the screen and I'll share an Excel screen and do it. So that will be easier. So let me show it how to do it in Excel. Yeah, so I'll write it down. Rest of the part, see Excel. So I'll share that screen now and the Excel sheet. Okay, so let's go ahead and I'll stop share this screen and I'll share my other screen. Yeah, probably it will come up soon. Like, can anyone confirm that you can see my Excel sheet? That would be helpful. Okay, so that's great. That is, we can see it. So it's your xn. This is your xn plus 1. Now it's like write the formula here in this xn plus 1 column. So probably let me start with xn equals to 0.5 as I mentioned. And now you can write it as the formula that I have derived. So it's this square plus 1 plus again xn, this times exponential of minus n. So this whole has to be divided by the expression, which is 2 times naught plus exponential of minus of this x naught. Okay. So this will give you the second value. So now what you can do, your 1 becomes this, and you will just copy and probably paste values here. Okay, that's causing some complication. Let me write it down, 721926. Then you just drag this formula here. We'll get the value for the next step. Then your n equals to 2. Write it 703601. You drag it here. You get the value for the next step. And you can also keep a check on like something like this. So if it's below a threshold, you will terminate. So I can write it as this minus this. Yeah, I can see that it's already very close. Now it's 0.703467. Yeah, so here probably we'll see that it's already less than 10 to the power minus 6. So your final answer is this one, 0.703467. Okay, so this is all about Newton-Raphson method. I think you can easily solve this problem. So I'll come back to the Excel sheet again. Uh, so let me go to the next problem meanwhile. So I'll again stop share this screen. and I'll go into solving the second problem. Yeah, so I think the screen is visible now. So my answer to this question was, so you can easily solve it using Excel. So that's all about Newton Raphson method. So one more thing I wanted to discuss here is that you have this formula, say xn plus 1 equals to xn minus fxn of f prime xn, something like that. So you can guess that whenever your denominator here becomes 0, you cannot use this formula to solve this problem. So one way of avoiding it is to use some other initialization and check from that. So that might solve the problem in most cases. So be careful while applying this formula. Okay, so let's discuss the next topic, which is the bracketing methods topic. So let's go into it. So first I'll talk about this exhaustive search method. Okay, so again, let's take an example. So your fx is say now x square plus 128 by x. So this now I have given you. So I'm telling you that find the interval where fx takes a minimum value. So it's like if you just shrink the interval as much as you can, that would be good. So using exhaustive uh, search method. And also let me give you the boundary points. So it's like your A, you can take it as 2, the B, you can take it as say 10, and let me take the number of intervals n equals to say 16. So let's try to solve this. So what will be the length of each interval? So can anyone tell me what delta x is in this problem? Yes, yes, that's correct. So I think it's pretty simple, this problem. So it's 10 minus 2 by 16. So it's 8 divided by 16, which is again 0.5. So this is my delta x. And what we typically do is in exhaustive search method, suppose we have some function like this. Uh, so can anyone tell me what this function is? There is a name for this function for which you can apply these methods, this exhaustive search methods or the other bracketing algorithms. No, it's I'm asking you about the name of the function. So suppose can your function be something like this? Yeah, universal. That's correct. So now I have defined it, say this interval. This is A, this is B, and I have taken some delta x. So what we can do is that we can start from here, take it as say x1, this is x2, this is x3, and all of this is delta x. So what you can do, you can take your x1 equals to 2, then your x2 becomes x1 plus delta x, which is 2 plus zero point 0.5, this is 2.5, and your x3 becomes x2 2 plus delta x, which is 2.5 plus 5, which is 3. So now what you have is you have this 3 points, and now you have to evaluate your functions at this 3 points. So what I have is x squared plus 128 by x. So your f x1 is your f2, so it's 2 square plus 128 by 2. Your f 2.5 is 2.5 square plus 128 by 2.5. Your f3 is 3 square plus 128 by 3. So I need to calculate these values. Again, I can use Excel, but since I have to again unshare the screen and use the other one, I'll just use a calculator just now, and I'll just tell you the values right now itself. So the first one is 68. Second one is, let me calculate it. I think it's simple. Yeah, it's 57.45. And the third one is, it will be, I think, somewhere in the range of 51. Yeah. So this is this. Oh, because I'm in two devices, so I'm not sure whether two screens I can share together. So that's why. Uh, so now, yes, I'll get to it. Anyway, I'm not doing it in Excel right now. When I do it, I'll show you that part as well. So that's not a problem. So anyway, you can calculate this value using calculator as well. So what you have is that you have this condition now. Your f2 is greater than f2.5, greater than f3. So now you cannot say for certain that whether your, okay, is my screen visible? Okay, now it has appeared. Yeah, so you cannot say for certain in which interval this minima lies, but you can say for sure that your delta has to be positive in case you get to this condition. So what you will do here in exhaustive search method, you will then set x1 to x2, x2 to x3. So earlier it was, I think, 2.5. This was 3. And your x3 now will become 3 plus zero point 0.5, which is delta x. So now it's 3.5. You have already evaluated your function values at 2.5 and 3. So now what you will do, you will get this f3.5. So this is 3.5 square plus 128 divided by 3.5. So this will again give you, so 128 divided by 3.5, so that's 48.82. Similarly, you can see that it's again lesser than what you had before. So you have to again go for F4. So your F4 will be 4 square plus 128 by 4. So I think this is 48. And again, it's lesser, but then you have to go for F4.5. So now, so when we calculate this value, we'll get something like 48.69. So now looking at this tree, can anyone tell me where the root lies, in which interval? So this condition is something. Uh, how can you say it's between these two? Uh, it might happen that it is around 4.1, 4.2. Why not? Uh, so let me give you an example. Suppose your minima is somewhere here, you have evaluated your function at, say, uh, if this is a 3.5, the leftmost point, this one is 4, this one is some arbitrary x, and here again, this is say 4.5 or something. You can say for certain that minima will occur somewhere between 3.5 and 4.5, but you don't know whether this minima has already occurred before 4 or after 4. So yeah, so that you need to understand. So always draw some sketch and try to understand this kind of problem. So your interval, the final answer in this case will be 3.5 and 4.5. And actually the minima will occur at x equals to 4. That you can find out easily, like I have given you the function x square plus 128 by x. So since it's pretty easy to derive the first derivative and the second derivative in this case, it's not required that you use this bracketing method. It's only for functions that we cannot use, but for understanding purpose, I have given you this easy example. So here you will get something like this, 128 divided by x square. And when you set this to 0, you will get uh, x cube equals to 64 and x naught equals to 0. Yeah? So one of the roots will be x equals to 4. And when you take the second derivative, you will see that it will be greater than 0 for at x equals to 4. So that's why you will get the minima at x equals to 4 here. So this way you can get to the exact minima point, but using that exhaustive search method, you can just bound it within some region. So this is one example of that exhausting search method. So next, go into another example, which is an example of the other technique, which is the bounding phase method. Yeah, so as before, I'm taking the same example. I'm not writing down the entire question. So now, can anyone tell me what's the difference between the exhaustive search method and this bounding phase method? There is just one difference between the two. Okay. Yeah, I hope you have not forgotten, but yeah, if you have forgot, then probably it will be a refresher when I explain it. So, what we do here also is that we have, say, a equals to 2, b equals to, say, 10, something like this. And we have some delta x given here. It's not like we'll take some equal intervals or what, but delta x will be given, say 0.5. So again, what we will do, you will calculate your f2. You will calculate your f2.5. And so what you will do, you will set your x1 to 2, x2 to 2.5. And when you evaluate this function, I think you have already you got this from the previous one as well. And also you can get your x3 as your 3. So again, you will check for similar conditions, but here the update rule is something which is different. So your update rule is that your xn plus 1 is xn times 2 to the power n times delta. Yeah, delta I would write, or delta x or something I can write. So this is the only part where this is different. So when you update, suppose you start with, say, some x naught, and when you evaluate x1, so it's x naught times 2 to the power 0 times delta x. This is x naught plus delta x. This is as before, which you had in the previous method. But when you get to the next updation, then that will be something like this: x1 plus 2 times delta x. The next tree will be x2 plus 4 times delta x. So it's like in every step you are the region that you are moving forward or probably backward in some cases, that you kind of expanding and trying to get to the interval pretty quickly. And once you kind of get one interval, you can further take some delta x, which is pretty less than what you had before. Like probably now you'll explore with 0.1 or something, and you can further that shrink that interval as well. So that's the idea behind this bounding phase method. So I'm not going into the detailed calculation for this problem again, because it will be pretty similar, and I have shown the calculations for the exhaustive search method already. So right now I'll pause and see if there is any doubts that you have, the three problems that we have discussed so far. Otherwise, I'll move forward to the next problem. Okay, so I hope there are no doubts. So let's try and let's see, we can solve another problem. I think now I'll go and solve this golden section search method problem, and other two are pretty similar. This Okay, okay. So you want me to like solve this for it? Yeah, yes, yes. Okay, okay. Sure, I'll solve it for you. Not a problem. Yeah, just a minute. Just confirm one thing. Yeah. So this third problem, what you can do, actually, I think I have written this part a little bit wrong, but this update rule that I have written is correct. So let's start with uh, what I can do. Let's see. Since it's defined between 2 and 10, let me take x naught equals to say 2.5. Now, your step 1 in this problem, yeah, take an initial guess, say x naught, I have given you as 2.5. Then your delta x that I have also given as 0.5. Yes, yes, you can draw a graph, that's fine, but for functions that are complicated, then it will be pretty difficult to figure out how the nature of the graph looks like and something like that. You can always draw it in some like some software or some website will draw it for you, but ultimately probably you won't be having access to that, and you can need to get to some sort of a solution which you can say for certain that lies in certain intervals. So that's why you go for this technique. So yeah, yeah, that I'm going to explain. That's true. So what you have to do, you have to evaluate your function at f x naught minus delta x, and then f x naught and f x naught plus delta x. So here what you have, yeah, if you look at the picture, this is x naught, this is x naught minus delta, and this is x naught plus delta x. Is that clear now? The picture and everything. So this part becomes your 2.5 minus 0.5. So this is F2. This part is your F2.5. And this is your F3. It's clear, right? Until now. So I have already calculated this value from the previous problem. So my F2 was 68 and next one is 57.45, these values, and 51.67. So what I have, it's this one is 68. This is probably 57 point something. This is 51 point something. So again, you need to check the order for this. So now if we have something like your fx naught minus delta x, this is greater than equals to fx naught, greater than equals to fx naught plus delta x, then you can say for certain that your delta x is positive. So that means you will kind of shift it to the positive side. And now what you will do, now you will apply your update rule. So this will become, you started with 2.5 and this will become 3. Again, you have to check for F3 and your F3, if this is again, say less than your F2.5, which was the case before when we solved the previous problem. What you do, you need to go back to this step again and update. So you will again do x2 equals x1 plus this. So this will become 3 plus 2 times 0.5, which is 4. Now you will check for F4 with respect to F3. So I think what was the value of F4? F4 was again less than F3. Yeah. So now what you have to do again, you have to again go back and just update. So your x3 is x2 plus 2 square delta x. So this will become 4 plus 4 times 0.6, 5. So this is 6. Now you calculate f6, and I'm pretty sure that when you calculate it, it will be your f6 will again be greater than f4. So now you can say for certain that your function lies, like your root lies somewhere in the interval 3 and 6. So that's how this minimum will lie in this interval, and you can further shrink this interval by taking some initial guess in this interval, and also just take some different value, the lesser value of delta, and try to shrink it further. So that's the idea behind this method. So I think it's clear now to you, probably. Uh, any other questions that you have? It's difficult means in what sense? It's only one thing that's different here. So suppose you have a function like this. Earlier, what you were doing, you were taking say 3 points and trying to like shift it in this direction and trying to reach here. This was in the exhaustive search method. Here also, you are doing the same thing, but in a different way. You are taking some x naught here, and again you are taking some delta and looking at like some other x naught minus delta and x naught plus delta. And again you are evaluating your function at these points only. And again you are determining whether you go this side or you had to move the other side. But in this case, you need not move in the left side. So you'll again go to this other side. But the difference is that next time you will have your x1 as this, x2 as this, something like this, and x3 as again something like this. Here, your shift might be different. So in the next step, when you update, you go from x0 to x1. So this will become this. But when you go to say x2, your x2 is not equals to x0 plus 2 delta in this case. I think it will be x0 plus 3 delta in this case, because you had one delta from before and then another 2 delta that you are adding. So it's the shift is which is different. So you're shifting it more and you are calculating the function value. So it's pretty subtle difference that you have here. But if you draw the picture and write it down, I think it would be easier for you to understand. Yeah, only one step is different here. Okay, so I think you will get it when you like solve it on your own with examples, easy examples. Okay, so yeah, so let me probably cover one more problem and then I'll be taking some questions if you have anything else related to the assignment. So I'll solve one question related to golden section search method. Let's see how much I can cover. So this is on golden section search method. So here also, suppose I give you one function fx, say it's sine x plus sine 2x, something like this. Some function I give you like this. Now I tell you using this golden section search method, find, suppose I give you this interval 0 to pi by 2, so your x belongs to this interval. So find where fx attains maximum value in this interval. So in golden section search method, what we'll do again, suppose need not be the function that I have given you. So this function's nature will be different. I'll just give you an example with a different curve. So suppose this is your A, this is your B. This you can also write it as XL, which is the lower bound, lower limit, we can say, or this is the upper limit of this interval. Now, what you do, you take, so this entire length, you can take it as L, and then you will calculate something like this. This is tau times uh, B minus A. And again, from this side, you can take something similar, which is tau times B minus A. This point you name it as x1, this point you name it as x2. And your tau value is, I think, around 0.618 or something. This you can already like calculate. So I think there was a proof of this in the slides also when Sir taught this golden section search method. So that you don't over calculate things. Next time when you take the other interval, you kind of get into the same point or something like that, through which you can prove it. So in this case, what we'll do, you can create one table, something like this, and then I'll probably show it quickly in Excel if I have time. So you have A, B, x1, x2, fx1, fx2. Then one condition that you need to check that I'll be mentioning, then you will take A minus B, and then you will calculate A plus B by 2. So I think there was a mistake in the slide. It was written as A minus B by 2, but it should not be the case. You just take the average of A and B, and that's what you need to do here, ultimately when you shrink the interval. So in this case, in this problem, my A and B are given. So it's A is 0, B is pi by 2, which you can write it as 1.57, something like this, if you take pi equals to 3.14. Now, you need to know your x1 and x2. So how to get that? I have already shown you in the figure that your x1 is nothing but your A plus tau times B minus A. So your A is here 0, the tau is 0.618, and your B is pi by 2 minus 0. So you can calculate your x1 using this. Then you calculate x2, which is B minus tau times B minus A, which you were shifting from the right side. So this is pi by 2 minus 0.618. This is uh, this you can calculate. So now after getting x1 and x2, you can plug those in the function expression that I have given. And now next you have to check for one condition and you have to eliminate some region. So that's the um, goal in this region elimination technique. So suppose you have a minimization problem. Now suppose your function, if here this is say x1 and say this is your x2, so you have your fx1 here, fx2 here. So this is your fx1, this is fx2. So this condition is fx1 greater than fx2. So in this situation, what you can say for certain is that nothing will be there in this portion. So if this is A, then you can just eliminate this part and you can work with the rest of the portion to see the minimalize in that region or not. So that will be true in case of this unimodal functions. And so this is you eliminate. Similarly, it might happen that your or probably I have done something wrong. Let me check. Yeah, I think your x1 should be in that side only. Let me modify it a little bit. So in golden section search method, yeah, so let's name it as x2 and probably your x1, which will be greater, your x1 would be around this region and probably this value is greater. So yeah, your and probably this is your b. So minima will be from x2 to b. That you can say for certain. So I had written it wrongly before because x1 should be probably in this side because you are taking 0.618 times of that L that you are shifting. So again, similarly, if the reverse things happen, so suppose your x1 is somewhere here and x2 is somewhere here, and this is your b, this is your a, and if your fx2 is greater than fx1, in this case, what you can say for certain is that this part you can eliminate because you will have a kind of increasing trend from this region, and you can just eliminate this part and check in the rest of the part whether the minima occurs there or not. Your x2 could have been here as well, so that's why you could cannot eliminate the rest of the part that I have talked about, or probably here. Yeah. So that's the idea behind it. So you have to check it through these conditions. Let me just check once I've written this correctly. Uh, yeah, so when your fx1 is greater than fx2, what you do is your b will become, or probably I've written it wrongly. Yeah, okay, so yeah, I think I made one mistake. Yeah, that's fine. Anyway, I think refer to the slides only. I think I've drawn something wrong here. So when your fx1 is greater than fx2, you set your a equals to a and b equals to x1. So essentially you are eliminating, I think, this portion. And when the opposite thing happens, you have to eliminate the other portion. You set your a equals to x2 and b equals to b. So you have to eliminate this portion. Yeah, I think if I draw the picture correctly, yeah, so because your x1 can be here as well, so you cannot eliminate the right portion because your minima will lie here. Here also you are satisfying fx2 greater than fx1. Yeah, so because of the drawing, I made that mistake. So yeah, please pay attention to it when you do it as well. Don't make mistakes like me. So let's me see how much time I have. I have 10 minutes. So you can set this up in Excel and you can solve it. And this condition you have to check whether f1 is greater than f2 or f2 is greater than f1. And after that, you have to adjust your A and B accordingly. So let me see at this moment if you have like any doubts because I'm not sure if I'll be able to complete this problem. Uh, Otherwise, I'll quickly show it in Excel in 5 minutes probably. So I guess that will be good. Okay, so I'll stop sharing this. Yeah, I'll quickly show you. Yeah, I think you were able to see it, but probably I need to zoom in a bit. Okay. Yes, so that was for the previous problem. Oh, sorry. So for this problem, what I can do, let me take this example, this table quickly. Yeah, so A, B, x1, x2, f of x1. This condition you need to check. Then you have then you have something like this. So I had this as this is pi by 2, and your x1 will be your A. So this formula you can write it down here. A plus 0.618 times the difference between these two. So it's B minus A. So this way you can calculate, and your x2 is B minus 0.618 times B minus A. So now you have to get the function values. So your function is sine x plus sine 2x. So this is x1, so sine x. And it will take it in radians only, so that's not a problem. So this is 2x. So this is your function value. Again, you have to do write it sine x plus sine call this, yeah, 2 6. Okay. Yeah, so now you can see your f1 is greater than f2. So this you can write like f1 greater than f2. This difference is again this minus, sorry, yeah. So this will be this minus this. Yeah, the modulus I'm not showing it right now. That's fine. Can fix it later. And also this will be divided by 2. Yeah, so next you will have to revise your A and B accordingly. So I think I've written as your A will remain unchanged when your F1 is greater than F2. No, we are solving a maximization problem here. So I think the conditions will reverse. So your F1 will be changed to X2. So this will be this. Yeah, so be careful when you solve a maximization problem or a minimization problem, so something like that. And then you can just drag this formula here. So it will automatically calculate you the next update for you. Yeah, something like this. Now you have a different condition, F2 greater than F1. This again you can drag and calculate. Yeah. Next, again, since this condition has reversed now, this A will remain unchanged, and you have to adjust your B to this X1 value. So it will be around 1.1997. And then again, you can just drag this rest of the part accordingly. Then again, your condition, your fx1 and fx2 now are very close to each other. And it's like this. Again, this portion, you can drag it. Yeah, this you need to again revise to x2, say 2921. This B part will remain as it is. Now, what you have to do, yeah, now your F2 has become greater than F1. So this way you can solve this problem. So I'm not going into the detail of it now because I think that should be clear when you do it yourself as well. So I'll stop here because it's almost 4. So let me see if there are any questions related to assignment or anything. Any doubts related to the assignment? Yes, I think there are few questions in the assignment which is confusing, and probably there are some typos, so we understand that. So we'll talk with the main T of this course, and probably those questions will be either will be modified or probably will not be evaluated. So that's not a problem. Okay. Yeah. So just be careful when you solve a maximization problem because the curve will change in that case. So let me see if I still have 2 minutes of my time. Yeah, when you solve those maximization problems, the curve will be like this. Now you're maximized somewhere here. You are evaluating your x1 here and probably your x2 here. So this is x2, this is x1. Now your f1 is greater than f2, but earlier what we said, we'll set a to this. So earlier probably we said we'll eliminate the other region, but if your x1 is somewhere here, then you cannot eliminate this right portion. This right portion, you need to keep it because you're maximized here. So you can eliminate this part. So this condition changes now. Your x2 becomes a and your b remains b in the next iteration. So be careful with that. And probably you'll get some questions like that in the assignment as well. Yeah. So that what I was doing in the Excel example also. I was setting my A and B accordingly by looking at the conditions. So it's almost 4. So if anyone has a question, they can stay back. Otherwise, they can join the other session that's from 4 to 5. The other two will take that session.